Well, this may seem a little perfunctory or untimely to introduce somebody we've just spent 30 minutes listening to. But we did, I notice a few folks joined us a little bit belatedly, so I'll proceed just the same. Again, good evening, and thank you for joining us. My name is Chris Brown, the Deputy Director of the National Air and Space Museum. And on behalf of General Daly, the museum's John and Madrian Mars Director, and the entire team at the museum, I want to welcome you to this year's annual John and Bahcall Distinguished Lecture Series. This signature event has been held since 2007, providing inspiration to its audience for the last 10 years. As most, if not all of you know, John Bahcall was one of the movers and shakers behind the creation of the Hubble telescope. Netta Bahcall, John's widow and the Eugene Higgins Professor of Astrophysics at Princeton University, has regularly attended this lecture. She's unable to join us tonight, but is watching from home. We'd like to thank you, Professor Bahcall, for your support and for joining us this evening. We also want to thank the Space Telescope Science Institute and the Hubble Space Telescope Project, NASA Goddard Space Flight Center, for supporting this event. Our speaker tonight, whom some of you, or most everyone, has just heard from in our opening Meet the Lecturer session, really requires no introduction, but certainly deserves one. As you will soon hear described, it took over 1,000 physicists to build a device capable of detecting vibrations in space and time known as gravity waves coming from the merger of two monstrous black holes. MIT's Ray Weiss was the team's inspirational leader and guide and will speak about this human triumph. Dr. Weiss was trained in physics at MIT and after appointments at Tufts and Princeton, returned to MIT in 1964, rising in the ranks to become one of the most respected names in physics, astrophysics, and cosmology. He was a guiding light in the development of the Cosmic Microwave Background Radiation Project, the NASA satellite that first explained the structure in the Big Bang, and he has been an intellectual and instrumental leader for the LIGO collaboration involving some 1,000 physicists from 130 institutions across the globe. Honors bestowed upon him are too numerous to list, but perhaps among his most treasured accomplishments is the outstanding teaching reputation he has earned at MIT and beyond. And as a member of the National Academy of Sciences, he has served on some 9 major committees, literally plotting the course of scientific life in America. Tonight, he will give us a personal glimpse into one of the greatest human intellectual conquests of our day, catching a wave in space and time. Thank you.
Wow, wow, wow. Okay. Yeah, all right. With an introduction, I'm embarrassed now. This has to be a good lecture, right? I'm going to tell you a little about what was going on 100 years ago first, and maybe even longer than that. And the idea that suddenly we have now discovered gravitational waves goes way back to 1915 and 1916. And I'll tell you a little about that. It goes back to Albert Einstein. But first, let's talk about Newton. And Newton is actually as important as any scientist you'll ever run into in terms of the scientific revolution. Because what Newton did is he did something which we should all admire if you haven't thought about it in a deep way. And that is, he took something which is like gravity, and I will try to point this equation right here. That's Newton, by the way. That equation, I don't know if you can see this green thing, but is the basic equation of gravity in Newton's theory. And what it is, it says that there's a force that's a gravitational force that is determined by two masses that are attracting each other. The mass of one, mass of the other, is a constant. And then it gets weaker as you go with the square of the distance between those objects. And that was a actually wonderful observation that Newton made. In it, he was able to explain how it was that the moon actually was tied to the Earth. And with that, he solved a problem which was a piece of universal science. Something which is, that was a brand new idea at the time, namely that you couple things that are going on in outer space with things that are going on the Earth, and that they have a universal relationship that you can understand, and it isn't some sort of foolishness. It's something that you can rely on. Now, what's wrong with it is that in the end, it turned out that you can get a long way with Newton's laws of gravity. What's wrong with it is that it doesn't work in two places well enough. And one of them is in the idea that when things get to moving very fast, the gravitational waves are not, the gravitation is not explained anymore by this. But the other thing is that it doesn't explain a communication between objects that is called gravitational waves. And this is what Einstein then brought into the system. And this equation is a much more complicated looking thing. We're not going to do much with it, except I'm going to try to tell you what it says. And then I'll try to give you an example of it. What's going on here is that what this is it says, look, there's a relationship between the space and time, and we'll say you see more about that, in a gravitational field, which is the side on this side of this equation, and the distribution of matter and energy. In other words, the geometry of space and time is determined by the distribution of mass and energy. And that doesn't smell like F equals ma or anything what Newton did, but it's a profound new idea. And it embodies the idea that gravity is becomes part of geometry, which was, and I'll try to make that a little clearer by showing you an example. And here, the way you can think of this is how many of you know what a jungle gym is? Most of you know what a jungle gym is. Good. Well, anyway, what it is you're taking you're making a system of a jungle gym, and you're laying it out so that everywhere you have a bar that's going in, let's say, in the X direction, and another bar going in the Y direction, another bar going in the Z direction, and just like the jungle gym that you have in the playground. And now what you do is you have made it so that you have put clocks at every intersection point in the jungle gym. And what you will find, and this is the new way of thinking about gravity, a la Einstein and those equations, is that the time that's kept by clocks in the system is dependent on where there are masses, and the way space is measured is dependent where you put masses. So for example, here's this jungle gym beautifully laid out. You're cutting through it in two dimensions. There are more dimensions in both directions, but it's too hard to draw 4 dimensions. You can't do that. So we're just doing it in 2 dimensions here. And what happens is that here is the sun. You put that into the system, and what it has done is it's taken space and changed the way you measure space against the way you started it. Namely, you've laid out coordinates, and now it turns out that lines that were straight lines become curved lines. The other thing that's happened in this thing, and here's the Earth, for example. That's got a little dimple that it made into this space. And on top of that, although it's not shown in the picture, there are places all along the way where you put clocks. All these intersection points, a huge array of clocks. And all those clocks read exactly the same time at the same moment of time. It's not something you can do by looking at a picture, because if you do that, you'll find out that the clocks that are near you read a different time than the ones that are far away from you, because it took different lengths of time for the light or the images of those clocks to get to you. So you have to go around and establish that by going everywhere and establishing at every intersection point where you put a clock does indeed read the same time. And so now, this is the description of Einstein's way of looking at gravity. It's a distortion of space and time, okay, by the objects that have been put into it. And that's what we're going to be talking about as, in fact, we're going to be talking about what we measured in this experiment that LIGO did, or the gravitational wave experiment. We're going to talk about that as being interpreted as a distortion of that space by the objects that were put into it. And we're going to try to measure that. So the first people that, in my book, that actually tried to do this and they didn't realize they were doing it are these two. This is Russell Hulse, who was a graduate student at University of Massachusetts in Amherst at the time, and Joe Taylor, who was a professor there at the time. And they did something, they found something which is really quite dramatic. What they found was the following. They couldn't see this with their eyes. They were doing radio telescopes. They were using radio observations. And they found a system, which is depicted here, which consisted of a pulsar, and I'll explain that in a second. And what they noticed, they were looking at the periodicity of this pulsar and that one. These are two objects that are tied together gravitationally. Both of them are pulsars. Now, what's a pulsar? They are stars that weigh what the sun does. It's big, 10 to the 33 grams, okay, 10 to 31 kilograms. And they are, they are about the size of Greater Washington. That's about it. In other words, they're a whole star, like our sun, in a volume no larger than delimited by a radius like that of the diameter, or the diameter of Washington. So it turns out they're enormously dense, and they have the density of nuclear matter. And so what they were seeing was this. This is what they were seeing. And this particular star, and I can hardly see my green light here. That star, turns out it was a pulsar. It's a star that gives you a pulse every 17 times a second. It gives you a pulse. So it goes brrr like that. And it wasn't doing it absolutely steadily. It was doing it a little faster for about 4 hours, and then it was doing it a little more slowly for 4 hours. That's the first observation they made of this system. And they found, well, one way they eventually made a model of it, and they found that they really were two stars, this guy and that guy, and they were going around each other. And in fact, what was going on is this fellow, the whole system was turning around like that. And when it was moving toward you, it was going a little slower. I mean, toward you it was going a little faster, these pulses, and when they were going away from you, they were going a little slower. And that is the first discovery of what's called a binary star system, two stars going around each other. And they were able to do it all by listening to their radio signals. That's the way they did it. And they saw that it took it 8 hours to go around once. And here's the remarkable observation they made. They made a whole bunch of observations which are very interesting. But the most interesting one for our talk today is what they plotted is the fact that every time it went around once, these things went a little faster. In other words, the next go was a little shorter. The next time around was a little shorter again, shorter again. The orbit was always getting shorter in time. And that's what this plot is over here. This is in epoch right there. It's 1973, sort of, when they discovered the system. And then it goes on past 2000, but here's a plot they made. And this is the time, the change in time after each orbit. And it's a negative number because it's getting shorter and shorter. The time for one orbit is getting shorter and shorter. And here are the dots that are these are the data points. All of these points are data points. And what they passed through it is a curve. It was not fitted. It's just a curve once they knew the parameters for the system. And that shows that it's fitting some theory. And what the theory is these systems were speeding up. They were getting faster and faster due to the fact that they were radiating away gravitational energy. They were radiating away, in fact, they were radiating gravitational waves. And that was the first discovery that was made, the very first evidence we had of gravitational waves in our universe. And they won the Nobel Prize for that, and rightfully so. So, okay, so that was the dramatic observation of gravitational waves by an astrophysical system, and it was done by Hulse and Taylor. Now let me describe a little bit, and don't look at this, look at me. It'll make you dizzy. What this is, and we'll talk about that in a minute, is what actually the gravitational waves that were radiated by that system might look like. And what it is you're looking here at the waves coming out at you or going into the screen. Okay? And what you'll notice is you'll see a whole bunch of dots, and they're changing spacing. And now let's get a little into this. This is what a gravitational wave looks like and what it does to space. So, okay, again, I'm having trouble seeing this thing up here. Yeah, that's not so easy. Here's a place that's standing still. That's you, right there. You're standing still. And you'll notice this interesting pattern that let's take these two that dot, and that dot, they're moving a little bit. But to take on that same line, the furthest dots away, they're moving a lot. Okay? So the amount of motion has something to do with their separation. And what are those dots? Those are just reference points laid out into space for this, what is a gravitational wave that is causing an expansion and a contraction in space, which is what that system that Hulson-Taylor found is doing. Now, there's an interesting thing in this pattern you'll notice. You'll notice that when there is an expansion in, let's say, this direction, there's a contraction in that direction, the alternate direction. So it's going this way and that way, and it keeps alternating. Okay. Now, the other thing you'll notice is that the amount of motion is bigger the further the objects are apart. And that pattern is a pattern of constant strain at any one moment. In other words, at any one moment, that whole picture has a strain, this change in space, and there is the change in position divided by their separation is a constant at any one instant for all the things in this dimension and negative for them in all the things in dimension this way. So there's a stretching of space and a compression of space this way, and then it flips. Then there's a compression this way and a stretching of space that way. So this is a pattern then of what a gravitational wave looks like. It stretches space in one dimension, compresses it in the other, and that flips. And it's propagating at the velocity of light away from the source. I hope you have an image of what this might look like, okay? And so this is then a system that carries energy away from the objects themselves. And so the first person who actually tried to do something with this is Joseph Weber, who was a professor at the University of Maryland here in College Park. That's him. And what he was doing was he was trying to, he had come to the conclusion with John Wheeler's help that maybe it was possible to do an experiment to look for gravitational waves. In fact, just what I just showed you, the stretching of space in one dimension and the contraction of space in another traveling at the velocity of light. That's a gravitational wave. And so what he built is a device that he had at the University of Maryland right here. It was a great big bar. You can see there he is. It's bigger than him. And the bar had sensors on it that would sense just exactly what you saw in that picture, namely that it stretched the bar in one dimension and compressed it in another. So he has little sensors on here on the bar to do that. And it was a very ingenious idea. And he had one of these in the University of Maryland in College Park. Then he had another one in a golf course about 8 miles away from his office. And that he kept seeing things that looked to him like there was stretching of that bar. And the idea was that it was fast enough so that the stretching was such that it would leave the bar ringing. In other words, the stretching would be very fast, and then the bar would sing afterward, like as though it had been hit by a hammer. And then, because he had such success with this in the beginning and a lot of events, he also put one in Chicago at the Argonne National Laboratories. And that's what finally did it. In 1969, he wrote a paper, one of the more significant papers in physics, about the fact that he had discovered gravitational waves and a few of them per day. And they were all synchronous. The idea that the ones in Chicago happened at the same time as the ones that happened in Maryland. And then, as in science, what often happens, and it's a good thing that it happens that way, a lot of people got very excited about this and decided they would try to do it themselves, because that's the way science progresses. What you do is people all over the world, there were 5 or 6 other groups in the United States, some in Europe, some in Asia. They built the same devices that you just saw in that picture. And it slowly unfolded that nobody else saw what Joe Weber did, which was most unfortunate. And it's a lovely way of showing how science rectifies itself. In other words, there was a mistake made somewhere, and other people were able to test it and find out that they didn't see it. And that is a statement of progress. And so it turns out that led to quite a whole bunch of circumstances of people getting into the field, trying to do it better, making it, but they all believed that maybe at some point or another people would see these gravitational waves. And so what came of it is that real calculations were made by theorists and also experimenters, but mostly theorists in this case, about what might be possible. What could you possibly imagine would be the kind of strain that is measurable from a gravitational wave. And people became convinced, and here's one of the people who was deeply involved in that, is Kip Thorne, who was at Caltech at the time, was deeply convinced that the largest you would ever expect to see, I can't tell if I get this pointer up there, is a change in length divided by length of about 10 to the minus 21. Now, for those of you who don't like these exponentials, let me quickly guide you down here. It's a lovely way to write powers of 10, okay? Here, so you can be with me. When I say 10 to the 3, okay, that means I'm multiplying 10 3 times, and I get 1,000, okay? It's a compact way of writing a big number. You say 10 to the power 3, 3 times multiplying 10. Or if you have a small number, that's putting it in the denominator. That minus sign puts it in the denominator. So 10 to the minus 3 is in the denominator now, 10 times 10 times 10. And so you're dealing with a number that is much, much less than 1, namely 0.001. Are you with me with this? Because that's important. I don't want to have to say billions and trillions, because I get all lost with quintillion. I don't know how to, it doesn't mean anything. So in other words, what we're dealing with is a change of length divided by a length of 10 to the minus 21 is the kind of estimate that people who began to look at this thing reasonably began to think was possible. Now, that's a terribly small number, and I'm now going to spend some time impressing you about the size of that number so you can appreciate why it was a complicated thing to do this. So another way to say it is the change in length. If you have 4 kilometers, suppose your length is 4 kilometers. The change in length associated with that, 10 to the minus 21, is about 4 times 10 to the minus 18 meters. Okay, now I'll show you more so you get that feeling in your guts. You got to understand this, because that's where the whole story is. So delta L, for example, is if you use light, it's about 10 to the minus 12 of the wavelength of light. In other words, you're looking at 0.011 zeros and then a 1, 0.0011 zeros and a 1 times the wavelength of light. And we'll talk about that more. That's one way of thinking about this delta L being that small. Or you're talking about the vibrations at the Earth's surface. How much vibration is it? It's 10 to the minus 12 of the vibration of the Earth at surface. We'll talk more about that. So all of a sudden, what's happened is you're dealing with something which is really remarkably small. And as I'll show you later, gravitational waves, if you want to ever detect them, are looking at the tiniest motions that people have ever done of things en masse. Okay, so here's sort of a way of getting you into it a little bit. Let's take a meter. In our country, we don't deal with meters. I wish we did. But a meter is about that. It's about 3 feet. And here's a hierarchy that gets you from where we are for something that's a meter down to where we want to be down here. So you start and you say, how big is your hair? Well, that's 10,000 times smaller than 1 meter. And then you say, okay, what's the wavelength of light, which is that next step? I can't see the spot. There it is. It's 100 times smaller again. You can determine the wavelength of light very easily for yourself. It's trivial. What you do is you can get this a simple little experiment you do when you go home. To make a little slit with your fingers. Look through your fingers and look at a yellow light or a mercury light, a green light. Make sure it's far away. And you'll notice little dark bands, black and green bands, through your fingers. Just do it. And if you do the geometry of that, you will then notice that you're dealing with something that's of the order of 10 to the minus 10 meters. But that's still way too big. So, okay. Next thing is you go down to atomic diameter. Well, okay, that's 10 to the minus 10 meters. That's another factor of 10,000. And you can prove that to yourself, too. And the way you do that, and I wish you would if you have any interest in this at all, you have a medicine dropper. Fill your bathtub up with water. It's an experiment you can do. Fill the medicine dropper up with some oil, any dishwashing fluid or anything, oil, a little bit of anything that just floats on top of water. And then measure the drop as you drop out of your dropper, medicine dropper. Look at the diameter of the drop. That tells you the volume of the stuff. If you know a little bit of geometry, because it's the cube of the drop. And then watch the splash you make in the water. okay? And the splash you make in the water has the same volume as that little drop does, but it's spread out, and it's going to be 1 atom high. In other words, the way you get that is make sure the drop has the same volume as the height of that thing and times the area of that splotch you can measure in the bathtub or wherever you do it. And you will get something like that number, 10 to the minus 10. Okay, that's the height, but that's as far as you can go on your own. Okay, and then the next thing is, well, okay, then you have to just believe me or deal with it. Whoops. Whoa. I wish I was using my computer. I'd rather wish I had. Okay. Anyway, so now you go down another 100,000. You get down to nuclear diameter of the nucleus, the diameter of a nucleus in an atom, 10 to the minus 15. You're still not there, and you have to go another 1,000 times smaller, and finally you get down to 10 to the minus 18. So I'm telling you, I hope to try to have given you some feel that you're measuring something exceedingly small. That's what the problem has been all along. Okay, so how do you do it? And I'll give you this is a little animation which shows you how it's done. It's not very hard to understand, I hope. And I'll look at you to see if I can when I get done. This is a laser. It's not a laser, but it's a make-believe laser. Here's something called a beam splitter, which divides the light. Some of it gets reflected, and it goes to that mirror. Some of it gets transmitted through this and goes to that mirror, comes back. And some of it then goes back to the laser. Some of it goes to a place where you put a detector. So let me show you what goes on. And this is how you do the measurement. And think of the beam splitter, that beam splitter, this thing right here, that at that place where I had the red square with all the dots that were expanding and contracting. That's you, okay? So now I hope I can make this work without it bombing on me. Okay. So there it is. And here the red is where there's light. And this is the wavelength of light. It's traveling wave. It hits the mirror. Same thing is happening on the other arm, which we'll see in a minute. Same thing is coming back. And now you'll notice over here the two lights cancel each other. There's no red here because they have spent the same time in both arms. And now what happens is one of these gets stretched and one gets expanded, just like those dots did in the picture of the gravitational wave that was coming out of the boards. And that's how you detect the gravitational wave. You look for the change. One arm gets longer, the other arm gets shorter, and you will see light show up when they're no longer exactly equal in length. And that's all there's to it. There's no more complicated than that. Now, who's lost me? That thing you just saw is called an interferometer. That's what that's called. It's a device that allows you to make measurements like that. And so that is the basis of, in fact, the LIGO detector. And now here is a picture of the people and who actually thought this thing all through. And what you see here is, for example, the device that was sort of the most primitive device that first did this. Here's the laser. And I just want to show you what some of the ideas that had to be done. We won't do everything. Laser, and then there's that splitter, that beam splitter, and then the light gets pushed back and forth many times. It passes this sort of 100 times. It does that in this arm. That's a way of gaining sensitivity by having the light go back and forth. And these are hanging masses. Everything is hanging so that you're not attached to the ground. Well, I'll show you why that's important in a minute. And that then is sort of was the basic idea. And then that was done at MIT first by these people. And one of them, some of them are still around. Jeff Livis is here at Goddard. Dan Dewey's retired. And David Shoemaker is now worrying about another project we'll get to at the end called LISA. And then the thing was really developed by the people on the very top, the German group. There is a guy named Hans Billings right there who has a Weber bar, the same kind of thing a Weber had, but they converted to this because they saw the promise of it. And they came up with all sorts of different inventions for this. And then a group in Scotland, here's Ron Drever, who was my colleague and saw this thing through. Unfortunately, he just died fairly recently. And he had a group of people in Scotland all making improvements on this, leading to this idea. And that's the detector that actually made the detections. And here you can recognize some of what you saw before. Here's the beam splitter. That's the place where you're standing in that mock-up. Here's the laser. This is a new thing. We'll talk about that in a minute. There's that distant mirror right there. And there's the other distant mirror. So that's the basic thing I showed you. But now you're going to see some extra mirrors in here. This mirror is a mirror that allows the light to leave here and bounce back and forth many times. And it does the same thing in both arms. So the time spent by light in this arm bouncing back and forth and in this arm bouncing back and forth is exactly the same. And now here are the two mirrors that are new and interesting. And this one is an idea that you take the light when there's no light going to the photodetector, like I showed you in the case when the paths were exactly equal. All the light out of the interferometer that comes from the laser has to come back to the laser. That's where it goes. And you do something tricky here. What you do is you do something called, you take the light that's coming back out of the interferometer, heading toward the laser, and you put another mirror right here, which does the following. What it does is it takes the laser light, and it reflects a little bit of it, because this is a mirror, but a partially transmitting mirror. And all the light that comes back from the interferometer, which is almost all the light that ever was put into it, is coming back through this mirror also. And those two beams, I haven't shown them to you, you arrange it so that the transmission of this mirror and the position of that mirror is such that all the light that comes back out of the interferometer is added to the light that goes into it, and nothing comes back and reflects to the laser. In other words, you make a little interferometer there again. And so all the light that is put out by the laser goes into this system. And that builds up the light in here by a huge amount. You might have 25 watts coming out of the laser. And in here, in this little cavity, you might have something like several kilowatts of light. And in these cavities, you might have half a megawatt of light. And that's how you eventually build up the sensitivity so that you can make these very, very detections of these very tiny amounts of motion. And you're using light to do it. And that's where you get that first factor of 10 to the 12 by having done these tricks. Now, there's another thing which is in here which I haven't explained to you, which is this mirror. And I'll leave that as you can ask me questions about it if you care to at the end. But what that does is it allows the sidebands, or the light that's generated by this not being balanced anymore, as a gravitational wave comes down and stretches these arms and shrinks them. There's no longer perfect cancellation to here, and that light can be fed back into the system for another go at it, and you can keep amplifying the light that was made, the light that didn't get balanced out, that didn't get reflected, that did not get canceled. You can build it up and thereby make the system sensitive at different frequencies. I know that's complicated, and I didn't describe it well. Ask me I don't want to go into any more detail at this moment. It's a way of tuning the spectral response of the instrument. Okay? These are all ideas that were generated by those people in the prior graph. Everybody added ideas to this and made it better and better. So here now is the other piece that you have to solve. And that was this business of how do you make sure that since you're living right here on the noisy Earth, that you are not being swamped by the fact that those mirrors, which are hanging somehow, that they are not being driven into motion separately by the Earth rather than by a gravitational wave. And I want to show you the idea. The idea is this. I don't know if you can see this. I wonder if they practice with this a little bit. This is a pendulum. I'm holding it in my right hand. That's the right hand up there. Is the ground. And what I'm going to show you is that at low frequencies, when I move this very slowly, this is the mirror that's going to reflect the light. That follows. They follow each other at low frequencies. You notice that? But if I move this quickly, faster than the period of the pendulum, this jiggles because I'm not doing it smoothly. But that doesn't move much. And in fact, that's the basis of the ground noise isolation. You do that with a pendulum. And you do it with a vengeance. You do that over and over again. And that's done over, whoops, okay. You got to get me back. Good, thank you. So what you do is you do it 4 times here. Here's the thing up on top. That's attached to the ground like my arm was. And there's the first pendulum. I can't see where this spot is, so you'll just have to count down. There are 4 pendulums in series. And the one at the bottom down here is the most isolated one of all, and that's the mirror that ultimately does the reflection. So that's one trick that you've got to use to get rid of the ground noise. But there's another trick, and a trick that's very similar to, well, how many of you have ever had earphones that cancel the noise on the outside when you're in an airplane? You know, you can hear the music, but you don't hear the airplane so well. It's the same idea. And the idea is to do something which is in this picture up here. And what's done is you have a sensor here. In the headphones, you have a microphone that listens to the airplane noise. Here, there's a sensor that measures the motion of a platform which is being isolated. Here's the ground, which is shaking up and down. And there's the platform, which is shaking a lot less. And here's a spring that isolates the two. And then you have a system which takes the output of a device that measures the motion in absolute space of that platform. It goes to here, feeds two coils that push this, and that push it just so that there is no motion of that platform. That's the idea. That's an active vibration isolation system. And it's something that is actually exportable from LIGO to other people. It's a very useful device. So with those two things together, you can then make the measurements against the noise on the surface of the Earth. I think I'll skip this slide. It just shows the two systems together. The top picture is that active system, and the bottom one is all those four pendula in series. So let's not waste time on that. So now let me talk a little bit about the discovery and how it was done. That's the device. We've talked about the device. And in the United States, at the time when this discovery was made, there were only two detectors actually working that had sensitivity for this. And one was in Louisiana, and the other one was in Washington State. And those are the two LIGO, the Laser Interferometer Gravitational Wave Observatory detectors. And let me walk you through, let me show you a little movie clip of what goes on up there. This is the two sites are different, but they are built identically. One is in a desert, and the other one is in a forest. So let me see if I can. Yeah, okay. Yeah. So that was the Louisiana Livingston. This is down in Washington State. This is down where there are trees is in Louisiana. Here's that beam tube which carries the laser light, all the laser beams inside of it. Here's a table that's very standard for people working with lasers. You know, you have to have lenses and actuators and stuff like that. And these are people in the control room learning how to run the system. And that's down in Louisiana, a picture of what people are who were trying to make this system operate. And okay. So let me tell you a little bit about the criteria now for detection. Okay? The criteria are actually, they're quite straightforward, and they are virtually the same as what Joe Weber used in his own way of doing this in the beginning. He didn't do it as carefully as this, and if you care to, I'll try to answer questions at the end about what people think Weber may have seen. I don't know that, but we didn't see it, nobody saw it. Okay? But I don't want to interfere with this. So the most important one is the bullet that's on top. And that is the waveform that you see. Whatever you see in one detector has got to be the same as what you see in the other. If they're not the same, or within the noise of the detectors, you throw the thing out. That's absolutely, and that's beautiful. You need to have that. That's the idea that Weber had too. The other thing is we had sensors at the two sites of all sorts of things one can think of that are in the environment. Like, for example, well, that list. So, things that measure the ground motion, things that measure the ground acceleration, things that measure the tilt, things that measure the acoustic noise, and so forth, all the way down all that whole list. I won't go through the whole list. You had independent sensors for these environmental parameters. And if any of those showed something at the same time as you saw a gravitational wave in the detectors, the two detectors, you nixed it. That was it. It was vetoed. Okay? And that was not the end yet. The thing that actually was a marvelous thing to have, and is one of the things you couldn't have done on a small scale, is that you furthermore had many, many signals coming out of the individual detectors at Louisiana and as also all in Washington State. And these are things that were signals that were used to establish that the detectors were operating properly. And for example, that the alignments were right, or that the laser frequency wasn't drifting, or that the laser amplitude wasn't being noisy, a set of things that are internal to the instruments. And you would use those signals to effectively look and see if they were doing something active. You wouldn't always throw the signal out because it may not be important, but you would at least know about that there was something strange going on in the apparatus at the same time as you saw what you thought was a gravitational wave signal coming in. So that was actually critical to this whole business. And one day, very early in the development of the newest detector in there, we saw this. And what you saw, let me just quickly walk you through this. This is a picture of a waveform. This is time down here from 0.25 seconds to 0.45 seconds. This is only 1/5 of a second from here to there. And on this axis is strain. And about the kind of thing that I didn't say that Kip Thorne and that, but that was implied. Kip Thorne and others had calculated for what should be able to be seen from astrophysical sources is about 1 × 10⁻21. The thing I tried to show you before, which had that, when I gave you the hierarchy of motions that you had to measure. And here you see this thing. This is noise. And slowly something emerges out of the noise. And there it is. And it gets faster and faster. And then all of a sudden it gets really quite big and noise-free, and then it's noise again. So that is a signal we saw on September 14th or 15th of 2015. And this was seen in Livingston. That was in Louisiana. Here's what was seen in Hanford. Again, noise. And this very similar kind of thing. Let me superpose them so that you can see how much they look the same. They're not identical because there's differences in the noise and the set. There's also slight differences in the sensitivity of the detector. They're not, and so, but here is the two signals superposed on each other, where you had to do the following. You had to slide one of the signals by 7/1000th of a second so that they could be on top of each other. In other words, what this tells us is that the signal that came, that we think is a gravitational wave, hit Louisiana first, and then it hit Washington State. So it came from the south. And that was, so that was very important to us. And in fact, that they looked sort of similar. And here then is another way to represent this. And this is as a function of time again. This is time versus frequency. And now frequency I'm talking about here is that those signals you saw, they're time-dependent signals. They get higher and higher frequency, as you can see. Now here's, let's say, this is the bottom of the piano, not quite. The bottom of the piano is about there. And this is middle C on the piano right there. Okay, you see the same picture on both sides. This is the one I can see best. And here is this time series again that we were talking about. And here is the amount of energy in the signal at each frequency. That goes with that scale on the left. And the same thing for the two sides. And let me play this for you as an audio signal so you can hear it. I thought I could, but we're not getting it. Okay, too bad. We're not going to waste time and make this work. But what it is you would have heard, had that worked. We tried it, but it didn't go. I don't know why not. What you would have heard, it would be like you had taken your hand and run it along the piano from the bottom of the piano and go like that, but very fast. So it would have been like whoop, like that. But if you speed it up, and that's what the second sound, and change the frequencies a little bit, so it would be a chirp. It'd go whoop, like that, whoop, just like that. And many signals that we've heard are like that. Now, many. Let me tell you what we think this is. Too bad the sound didn't work. It's just, it wasn't been that impressive anyway. Now, there was another miracle aside from the business of getting this apparatus working, and this is what this signal is about. What you're going to see now is a computer simulation of what we think. This is after the parameters. You fit the parameters. You look at the signals you have. You make your best fit using the Einstein field equations, the basic equations that Einstein predicted for general relativity. You should now know how to solve them, which is a miracle in its own right, but which is really a miracle is the fact that you know how to program it on a computer, and the computer programs don't blow up on you. And that took years and years and years. And what you're going to see now is just that thing you saw as data, as represented by what it is based on the theory. So this is now we think it's two black holes. Let me start this movie. I hope it runs. Yeah, and this is a computer simulation of this based on the data that came out. And what you're seeing is the two black dots that are going around each other are two black holes. And you're again taking that cut through just what I showed you in that jungle gym, that same cut we talked about before. And where the colors are, when it gets very red or black, that's the darker it gets, the slower the clocks are going. And those arrows that you see in there all over are effectively the stresses, or the strain effectively, in that medium, in this two-dimensional cut that we're taking here. And watch what happens as these things get losing their energy and as they get closer and closer. Very much like the Hulse-Taylor thing that we saw. And now you can look at this storm that's growing in the space. You can see that if you look down in that hole, you see that place where the clock stopped. Well, now they stopped the movie, just so you can see this. And it's now about to form a single black hole out of a pair of black holes. And there it is. And you can see now that everything quiets down. Those waves that are running away from it are the gravitational waves that we detected. And that's the best. And this is not a simulation that's drawn by an artist. This is a simulation made by a computer that's solving those equations I showed you in the second slide of this talk. It's not easy to do. And finally, as a breakthrough in the last 10 years with that. So that's what we think we were seeing. And here then is what we did see. Another way of presenting what we saw is this way. The very top one, this is again these, I'll point to the bottom one, but it applies to the top too. The vertical axis is the strain, here, the strain. And that, again, in units of 10 to the minus 21. And this is time again, okay? And these are waveforms. The very top one is the one we've been talking about. That's the short one. And that's one we're very sure of. This one happened a little later. It happened in October and of 2015. We're not so sure of that one. But we had to use a completely different data analysis technique to find this. This one we could see directly in the data. This guy right there. But this guy you had to do a lot of manipulation to find. And this one we're sure of. That's a very much longer thing. And it lasts a lot longer. And it's again, and this was seen in just a day after Christmas in that same year. And so here are some parameters that go with this. And I think the one that's most interesting is the big guy. And what you're talking about is 36 masses of the sun in one of those black holes against 29 masses of another in the other black hole. And they're colliding with each other, and they're losing 3 solar masses to gravitational waves. It's an unbelievable amount of energy that's going away. It's the brightest thing in the universe in terms of that moment, during that moment. Brighter than anything. Just the amount of power that's going out from these 2 black holes colliding with each other, making a new one. And these are more ordinary. For example, these are possible, these are black holes which are, people have experienced these before. These are pretty big ones. And the interesting one is this one. This number is sort of an interesting number. It says that if you put this same system not at 1 billion light years away, which is where it is, but put it where the sun is, okay, put this thing at the sun, okay? Well, all right, you'll notice a very interesting thing in this. That's 1 AU away. That's a distance about 1 distance from the sun away from the Earth. It turns out the strain that's associated with the change in length divided by the length is still pretty damn paltry. It's 10 to the minus 6. That means that you on the Earth would only been stretched by 1 micro inch compared to, every inch. It's nothing. But here comes the shocker. The amount of energy that's being carried away in power in the wave, the intensity in the wave, is 10 to the 25 watts per meter squared. Now, what in the hell does that mean? The sun is putting out 1 kilowatt, 1 times 10 to the 3 watts per meter squared in light when you get a sunburn. This is 10 to the 22 times more energy coming out than anything the sun puts out, okay, in power. And it tells you an interesting story. It tells you how stiff space is. Space does not like to make gravitational waves. In other words, it takes an enormous amount of energy per unit area, to make a gravitational wave, which still has this paltry amount of strain, the thing that you can measure at 10 to the minus 6. So that's that. So when this all happened, and we made the discovery in September of let's see, it was 2 years ago, okay. I'm having trouble with arithmetic all of a sudden. And, but anyway, I went to New York, and I was giving a talk someplace, and I noticed this thing in the subway. The one on the left, and I'll read it best from the screen here. It says that scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. Okay? I mean, and this was only about probably a month after we made the announcement that we had detected this. And then there's a New Yorker cartoon right on the right, and then one bird, the guy all the way out, saying, "Was that you I heard just now, or was it 2 black holes colliding?" Okay, so suddenly this thing became, a really amazing thing. And I said to myself, how did the public know to do this? And it turns out it's sort of an interesting story when you think about it, because Einstein is probably, when you ask a typical American who hasn't gone to some fancy college and say, name a scientist, they'll very often say Einstein, okay? And then you say black holes, and every kid in the world knows about black holes. They see it in the comic books. And the black holes, they're scary, they eat things, they eat you. And they make all sorts of trouble. So, you know, those people think they know about this. That's the thing. So it hit the public mind in a very interesting way. Now, I want to show you some people who are responsible for this. And here's Barry Barish, the one on the right. He was the head of the project for a while and made it actually happen. There were other heads, but also helped, but he was the most influential one. Then Stan Whitcomb, who was a scientist who was a chief scientist for the project. He said both of these are at Caltech. And Gary Sanders, who was a project manager. And then another guy who now is a deputy director of it and at Caltech. And here's the chief engineer of the project, Dennis Coyne. And the next slide shows you somewhat younger faces. These are people now who all were very important in this, as the ones who I showed you already. The people on this side are the people in the LIGO Scientific Collaboration, which is a group of about 70 different institutions, about 1,000 people. And these are the directors of the people who are voted as directors. Peter Salson, and then David Reitze, who is now director of the project, as well as having been the head of the LIGO Scientific Collaboration. And I hope many of you know Gabi Gonzalez, who was the current director until about a week ago. And then here are the people who are directors of the project. And that was Jay Marks. He followed Barry Barish, and David Reitze, who is the current director of the project. And then here are people who, you notice the faces are getting younger and younger as you go right. And here are the people, again, who actually made this detector work, the one with the fact that made the detection. And that's Dennis Coyne, who is the chief engineer of the project, Peter Fritschel, who is a young scientist at MIT, who helped write the paper, but is also the paper that was a discovery paper, but also is the chief scientist for the changes in the detector. And then David Shoemaker, who was sort of an engineer scientist that helped make the project happen, the new project, the advanced detector. And these two people are people at the site, Leo Froloff and Daniel Sigg, who actually were on site to do the commissioning, make the detector work. Okay, now I have another thing which I really have to say, and I don't mean to embarrass him. If he's here, I don't want to embarrass him, but I'm going to. And one thing you have to recognize, that this project was a project that was done in this town, really. It was the National Science Foundation, which is a remarkable organization that supported LIGO all the way from in the early 1970s, when it was just a brainchild, to the point where it had gone through many, many crises and but ultimately got to the point where it was being built. And there were, the fact is that here's what you have to recognize, that the Science Foundation, at the time when they began to look at this, saw that it was a very difficult project to do. They also saw that it had, if it worked, it would be quite transformative. It would change the way people thought about astrophysics, for example. It would also be a thing that would be a step for the future of thinking about how the universe is going to evolve. And so it turns out it had a risk, it had tremendous payoff, but it also had to be nourished in some way through a lot of things. And the NSF had the courage to see it through. And the man who helped that happen is Richard Isaacson, who's a picture right here. And his boss, Richard Isaacson convinced Marcel Barden, who was the head of physics, that this was not crazy. And somehow he managed to do it. It's amazing, okay? So, anyway, that is dedication. And why I have this other stuff in the slide, Rich wrote one of the more interesting papers, early papers, to show that gravitational radiation was real. It was very much debated all during the early history of the idea of general relativity having gravitational waves. And he happens to have a hobby, which is now consuming him, and a very nice hobby. He worries about Central Asian and Turkish cloth and the handicrafts of making rugs and different tent bands and things like that. Okay, so I'm almost done. I want to tell you where we are and what we are looking to the forward. So it turns out this picture is a picture of where in these three sources I showed you might they be in the sky. We're running again, by the way. We're seeing more sources. I can't tell you much about them yet. There's a lot of work that goes on in getting all that data together. But we're in another run now. But this is a result of that first run. And you can see this is a picture of the sky. I mean, this is an equatorial picture of the sky. Here's the sky equator, which is the same as the Earth's equator. And that's the North Pole and the South Pole, the same as. And this is where we think that source, the big guy that I spent a lot of time on, is. And the other one, which we thought was a good source but very small, is this. You give this to an astronomer and you say, go look for something that is analogous to what we find, and they look at you like you were out of your mind. I mean, you're saying, hey, this is huge. How can we search a thing like that? And so, but anyway, people do have the courage. Occasionally they do it. And we have a whole group of people who work with us. But it's not a good way to keep going. So we have to have all the other detectors that have been planned operating. And the thing is, there are other detectors that, in fact, they're the two we've been talking about in the United States. Then there's two in Italy. There's one in Italy, which is a French-Italian collaboration, which is a 3-kilometer detector. There's a research detector in Hanover, Germany. That's the same group that did some of the early work on doing the good ideas that were put into the field. And then there are 2 detectors that are in the process of being built. The one in Japan is going to be on the air, we hope, by about 2019, maybe 2020. And there's one being planned quite actively now in India. And the idea then is you can't use these detectors like a telescope. You can't point them. The way you find out where a source is by looking at the time difference of the arrival of the signals at these different places. And by homing in on that, you can tell better where it is on the sky. And you get maps that look something like this. This is the case, again, same kind of projection. This is the sky, the South Pole, North Pole, equatorial plane. And this is sort of the uncertainty if you had all 3 of the detectors, the 2 LIGO detectors and the one in Virgo, the one in Italy, running. And we hope to have that in this run that we're doing now. And you can see regions which are pretty good. These are uncertainty circles. This is sort of the size of the moon. But this is horrible. These are huge uncertainties. So one of the important things of having a detector in India, for example, or in Australia, but we were hoping Australia or India, but right now it looks like India, is that this is what happens if you add India to the detector in Hanford, which is the Washington one. This is the Indian detector, that's the Livingston one, and this is the one in Italy, the Virgo detector. And this is sort of the size of the moon. Most of these places are sort of the size of the moon. Still very uncomfortable for many very, very small telescopes. I mean, for very precise telescopes. But the size of a moon is at least, you can scan over that a lot better than over 1,000 square degrees, okay? So that's a very big difference in being able to identify where things are. And so here's my last slide. This is the way the field will unfold. And this is now showing you that LIGO is one part of a very large thing that's going to do science to open up this new field called gravitational wave astronomy. And what is in this picture is this is frequency of gravitational waves. And very, very top, I can't see it very well, is sort of benchmarks in time, the periods. And so here's LIGO, which has now made these detections of black hole pairs. It has other things it wants to look for, neutron star pairs. It wants to look for individual pulsars that are spinning around. It'll probably find all of these things. And this is sort of sensitive in the region from 10 hertz to about 10 kilohertz, or periods of 1/10 of a hertz to 10 to the minus 3, a tenth of a second to a 1,000th of a second, a little shorter than a 1,000th of a second. There's another project, which is as old almost as LIGO, which is to do this from space. And the idea is it's called LISA, the Laser Interferometer Space Antenna. And there's a very pretty orbit that's been designed for it. There's the sun, and this is the Earth orbit around the sun. 3 satellites going around in an equilateral triangle. And station keeping is quite easy, it turns out, in this particular orbit. And they hope to see black holes that are 10 to the 5 solar masses, not 30 or 40 solar masses, the ones like ones in our own galaxy. And also, they will probably see white dwarf binaries. These are ordinary stars all over our own galaxy that are going around each other. And they also hope to see small objects dropping into a big black hole. Those are very, very good for sensitive tests of general relativity. That project has had a complicated history, just like LIGO had in the beginning. And now I think it's back on track. There's hope for the United States to go back into it. It had dropped out of it. And the Europeans are part of it. They hope to launch this thing at in the 2030s, maybe as early as 2028 if they're lucky. And a lot depends on money. and what's left in Europe, what's left in the United States. Another project which is already going and on much longer wavelengths, much shorter, much lower frequencies, is the idea of tracking gravitational waves going through our own galaxy by radio astronomy. And that idea is very good. It's a nice idea. What you do is you use fast pulsars that are spinning at something like 600 times a second. Very fast. They're amazingly fast. And if you find enough of them, you find some in the northern part of the galaxy, some in the southern part of the galaxy, you find out, for example, if a gravitational wave is coming through, periods of a year, a few years, gravitational waves, but very, very long periods like that, going through our galaxy, you will see something interesting happen. The ones in the north will go, the pulsars will spin a little more slowly, and the one in the south will spin a little more slowly, but the ones in the east and the west, if you have enough of them, will spin faster. So you get a nice pattern, quadrupolar pattern, like that pattern of the stretching that I showed you. But at this time now, it's of the whole galaxy, and using the timing of the pulsars as a way of getting at this information. That project has been going for about 5, 6 years, longer than that, 10 years now, and they've pushed the limits down, but they haven't yet detected something. But if they detect something, it'll be gigantic black holes, 10 to 12, 10 to 11 solar mass black holes, and probably a background of gravitational waves from all of these heavy objects that is unresolved. And the last project is one you may have heard about. This is the one all the way to the over here, and it's much more complicated to explain, but I'll try. And what that is that how many of you know about a result that was going to be made, was made about 2 years ago, by the BICEP, it's called the BICEP collaboration. What it is a very interesting idea. The idea is, and it's to try to look at gravitational waves that were generated at the instant when the universe was formed. I'm talking about the instant, 10 to the minus 30 seconds. 10 to the minus 20, from 10 to the minus 30 to about 10 to the minus 25 seconds. If inflation is right, if that very modern idea that the universe was made out of a vacuum fluctuation is right, you should have gravitational waves, or you might have gravitational waves associated with that. Huge accelerations. And those will make gravitational waves which perturb the 3-degree background radiation, which we know and love. We know all about that. It'll perturb the polarization of that radiation. So by looking at the direction in which the electric fields are coming at us from the very late, much later epochs of the cosmic background radiation, the 3-degree background radiation, one can divine, by looking at patterns in that, whether there were gravitational waves that were there before the cosmic background electromagnetic radiation was formed. And that's the experiment that's being tried. And I hope they find something. And let me just do one last thing and show you the collaboration. This is I mentioned that in the beginning, I'm doing this on behalf of the collaboration. This is about, if you look through there's about 50, 60 institutions, 1,000 people, and they all are involved in some aspect of this. Some in the data analysis, some in the science, the way it's interpreted, and some very few, but very powerful individuals are involved with the detector itself. So it turns out it's hard to find experimenters. A lot of people who like to do computer programs. So thank you.
Did you want to field your own questions?
I'm happy, yeah.
Okay.
You got to turn the lights on. I got to see people. Yeah.
Okay. Might there be some questions? Well, let's see. Where do you want to start? Right in the middle here?
I hate to ask this, but what happened to the woman in Chicago?
Ha! What happened to the woman in Chicago? She got married, had 3 kids. Not mine, though.
I have a slightly different question. Can you say more about the laser power, the signal-to-noise ratio, the time resolution, the spatial resolution, things like that?
Okay. This was not supposed to be a technical talk. Mind you.
Asking more about the power of the laser.
Yeah, but I can tell you quickly. We're looking at motions of the test masses, these mirrors, of 10 to the minus 18 meters. Okay, so we use kilowatts out of we're using watts, hundreds of watts out of the laser. We hope to. Right now, you have about 50 watts out of the laser. It gets tricked up by all these mirrors that I showed you. And so we have sensitivity of about 10 to, by the time you get done doing all the photon statistics, And using squeezing, which we're going to be doing in the next go-around, which is a specific tailoring of the electromagnetic field that comes out of a laser. That's a special thing we do. We're not doing that yet, but we're planning on it. That we hope to get to about another 10 times better than what we are doing now in terms of the position sensitivity. In other words, the strain sensitivity. So instead of, right now you can see the noise is about 10 to the minus 19 meters per root hertz is sort of, that's 10 minus 19 meters in a bandwidth of a hertz. That's sort of the noise that we have right now. In much of the band, that's interesting. Not at higher frequencies, I don't think I want to show you the curves. Maybe we should talk privately about that. But so the thing is that we have to do a lot of work on the lasers to get this stabilized well enough to do that. I think I showed you how we do the actual the ground noise isolation. I did a better job of that than explaining the laser, the displacement sensitivity to you. The displacement sensitivity comes from the ability to break a fringe, in effect, to 10 to the minus 12 parts is really what we have to do. 10 to the 12 parts, so you have to break a fringe, a light fringe, into 10 to the 12 parts. That we've learned how to do better and better. And so our limit right now is pretty much two things. One of them is that we need to get rid of something which I haven't discussed with you at all, which is that there is thermal noise in the mirrors themselves. And I don't mean in the mirror bodies themselves, but in the coatings of the mirrors. It turns out, I haven't shown you the curves for that, but the coatings on the mirrors are noisy because they are lossy materials. And there's a lovely theorem called the fluctuation dissipation theorem in mathematics and physics, which says whatever puts the loss, mechanical loss into the system, is the thing that makes the thermal noise appear. And so right now we know that we are limited by the thermal noise in the coatings. We have to improve that. And that's work that's into the future. The work on improving the vibration isolation is, I don't think we have to do much more with that. I think we are at the level now that's good for the future. I don't know if I've answered you, but it's a continuing evolution, this whole thing. And we hope, for example, so you know, we hope to make, and I didn't show you that curve, but we hope to make we're not yet at design sensitivity. We're still a factor of 3 away from the design in amplitude. And then we have ideas how we're going to get another factor of 3 below that, and people are actually actively working on ideas of that. And then there's another idea to go, another factor of 10. And then we're probably at the point where we've run out of what we know how to do. So there's future, tremendous future yet.
Seems like there's plenty of room to move.
I didn't answer you properly. So if you want to learn more, come and talk to me, okay?
In the middle there.
Yeah.
I was wondering, is the spatial rigidity the same near Earth as it is far away?
Did you understand?
Is the spatial rigidity of an object the same near the Earth as it is far away from the Earth?
I'm into the space, the energy that it takes to squish. There's that 10 to the 25.
So is the rigidity of the space-time continuum?
Okay. I think what you're asking is this. You're not asking about the space, that space detector, are you? You're asking about the physics of how rigid is how hard is it to distort space.
That's right.
That's what you're asking about. And that number is the same wherever you are, whether you're near the Earth or you're near the beginning of the universe. What it is composed of, that number, which gives you the rigidity, which effectively is Young's modulus. I don't know the number offhand, but it's a set of fundamental constants. It involves the velocity of light, the velocity of light, and the frequencies. That's all it involves, and the masses of the objects that are moving. Okay, so it turns out the ratio of the power carried to the stiffness, which is a ratio, doesn't involve the mass, and that then is a number which is enormously stiff, and so I can't give you a Young's modulus for it. I should have been able to do that ahead of time. But you can get that from that formula I showed you, namely that 10 to the 24 watts per meter squared for a displacement of 10 to the minus 6, the delta L over L of 10 to the minus 6. So my guess that Young's modulus is in dynes per centimeter squared. It's somewhere around 10 to the 57, 58, something like that. It's a huge number. You don't squeeze space much. You just don't get it. But you have to make that number yourself. I'll make it for you, and give me your email, and I'll send it to you. Yeah.
In the blue.
Yeah.
These detectors are 4 kilometers long,
Yeah.
and you're looking for differences in, to measure 10 to the minus 21 meters?
No. You have it almost right. We're looking at a strain of 10 to the minus 21, which is a change in length divided by the length. And we're talking about movements at the ends, which are 10 to the minus 18 meters. Okay.
My question, though, is in the engineering of construction of the experiment, how do you get the mirrors to be that precisely the same distance on each arm
Okay.
away from the
Yeah. Thank you for that question.
So the question is, how do you position the mirrors that precisely?
You don't do that. You don't have to. Remember, what we're doing is we're looking for changes in time. So what we do is then that determines how the absolute spacing of the mirrors in 4 kilometers. We do want to get it pretty close because we don't want to be sensitive to the frequency noise of the detector, frequency noise of the laser. So in other words, if their path length differences are large, you get to be very sensitive to the frequency excursions of the laser. But we don't need to do that very well. We do that to a wavelength, maybe 10 to the minus 11, maybe 10 to the minus 6 meters, 10 to the minus 7 meters. No, we get to 10 to the minus 18 meters because we're looking changes that happen in times shorter than a tenth of a second. Okay?
Okay, behind you there was a question, but then I want to have a question over here. Yes. Yes, yes.
Does the gravitational lensing affect the frequency of the gravitational waves?
Yes. That's a good question. I like that question. Can I repeat it?
Yeah, please.
Does gravitational lensing affect gravitational waves the same way as it affects light? Is that a good way to say it? Yeah, and it does. In fact, that's when we get enough sources, and we will begin to see that effect. And in fact, that you see 2 things. You'll see, most likely, we won't see a change in frequency so much of the gravitational wave, but a delay in the arrival of the gravitational wave from the same source when you look at different aspects of the same lens. You know what I'm talking about? What I'm saying is most lenses are broken up. Most of these gravitational lenses are not single points. They're never exactly on axis with the galaxy that's doing the bending. The galaxy has always got structure in it. So you see little bits of things that are all related to each other that are all lensed. And they are, and with light, you see this very clearly. And radio waves, you see it very clearly. If you open and you look at a gravitational lensed object, you'll see the same signal in the different spots at different times because it takes different path lengths to you. Okay?
Question over here from this gentleman.
How strong is a black hole?
What's the question?
How strong is a black hole?
How strong is a black
How
hole?
strong is a black hole? Okay, let me say how strong a black hole is, at least from what I know. Okay? I've never visited a black hole. I don't think I want to. But what it is that a black hole, in principle, at some point what I'm about to tell you will no longer be valid. Okay? But in principle, and we'll see where it may no longer be valid. As you, as an astronaut, I suppose, go near a black hole, nothing terrible happens. You won't even notice much until all of a sudden you get past a point of no return. And that's the event horizon. And what happens is you suddenly feel that as you're moving in your spaceship toward this thing, your head gets, let's suppose you're going down, you're closer to the black hole with your feet than you are with your head. So the legs will get pulled more than the head will, okay? Because it's closer to the middle of the black hole. And so what happens is that gets stronger and stronger and stronger, and then something very unfortunate happens to you. You get torn to bits, okay? And then what happens is the bits of you even get torn to bits. Okay, as these changes, the force grows. At some point, that's got to stop. But nobody knows exactly how to deal with that. In other words, there's something called a singularity inside the black hole. And if you keep dropping in, that singularity exerts these very large gravitational forces on you. And at some point or another, we hope that quantum theory, the quantum theory of gravity, will have something to say we have a limit to that. But I can't tell you where that is. There are experts working on that, trying to figure out how strong a gravitational field you can still get inside of the black hole. I don't know the answer, personally. What?
100.
Okay.
Okay.
There's a wonderful story that you might find written by Larry Niven called Neutron Star, where he envisions just what you described.
Yeah.
So you might read that.
Yeah. I mean, there's one thing which is a real challenge, so you know, and that you don't walk out of here thinking that all the answers are known. The quantum theory of gravity, how do you make a quantum theory of gravity? That's not in good shape. We don't know how to do that.
Right.
Yeah.
Plenty of room. Plenty of room to grow.
Yeah.
In the yellow, yes.
So there are so many black holes and other things out in the universe that can be the sources of gravitational waves. And yet, as we've begun to see them, we see so few. What's causing the discrepancy between the small number that we see and the large number of
Okay, nice. Thank you for that question. It's a good question. It leads to the answer about the future. Let me repeat the question. Why do we see so few if there's so many out there? We see only 3 or 4. We've seen some more in this current run. I can't tell you exactly all about them. Really, the data is still being analyzed. But the thing is that what we've seen, what the sources, the big one that we talked about with you, is it about 1 billion light years away, okay? Now, when you say 1 billion light years, that sounds, yeah, it's very far away, but you're only looking at a z, that's the redshift distance, of about 0.1. In other words, you're looking at a volume of the universe which is 1,000th of the size of the whole universe. We're not there yet, okay? So it turns out what we fully expect is that as we improve the detector, and there's an important statement about how you improve it. It turns out we're sensitive. The LIGO measures the waveform. It measures the actual field from the gravitational wave sources, not the power. The power is a different thing. That's what your eye sees. But we are actually measuring the field, like if you were measuring the electric field in an electromagnetic wave. And that says that the field goes down only as 1 over the distance, not like 1 over the distance squared. So that's because we measure actually the excursions of the gravitational field strength that comes in the wave. So it turns out that right now we're at about z of 0.1. We have to go to get to the edge of the universe, that visible edge of the universe. We have to get to a z of at least 1, if not 6. And what turns out, and people think the first stars were made at a z of 6. That's a good bit further out. And what we fully expect is that with each time you increase the sensitivity, let's say by improving the detector by a factor of 2, just a factor of 2, we don't gain by 2 in the number of events we see. We gain by 8 because it's the extra volume of the universe we're picking up, assuming that the black holes are uniformly distributed in the universe. So, for example, what we fully expect and have the capability of in this experiment is to look at a field that is 3 times better than what we have now. We just have to understand what's wrong. And that says we should be able to see 3 cubed more sources. So instead of 1 every couple of months, we should see 1 every 2 days, or maybe even 1 every day. And that gets into the regime where you can begin to start doing statistics on the black holes. And in fact, with some of the advances people are thinking about for the future, you might get to the point where you're seeing something like an event every hour. So we're just starting the field. It's just beginning, okay?
I would like to ask a question
Sure,
to see
please.
if we can clarify that on
Yeah.
the statistics. In order for these gravitational waves to be generated, it has to be in a binary system.
Right.
Is that right?
That's right.
So there can be plenty of black holes out there, but if they're not in binary systems,
We don't see them.
you don't see them.
Yeah. We might, well, be careful with that. We might see them
Right.
being formed. I mean, in other words, it turns out that there are many sources I haven't told you about. I mean, for very first, we didn't expect to see black holes in the first go like this. In fact, nobody could predict for us how many black holes there are per unit volume of the universe, especially how many black hole pairs they are. But the thing is that we expected to see neutron stars first. We know about them, that Hulse-Taylor thing that I showed you in the very beginning of my talk. There's more of those, and we knew about that. And so we expect something like that. If we get to design sensitivity with this detector, we hope somewhere about something like 3 to 10 of those per year. We didn't expect to see black holes. Nobody could tell us how many binary black holes there were. But now that we know how much improvement we have to make to get to very high rates. And it isn't a dreadful amount more.
I'm seeing more and more hands, but in
Yeah.
the very back, last row, let's give the last row a chance.
As an audiophile, what do you think of the rapid, frequency radio bursts that they're using now for detection? Are you following along with that?
Yeah. You're asking me about what are the range of frequencies that are associated with these black hole events. And the one we picked the one that I showed you the most detail about, runs from about, within our band, from 30 hertz to about 250 hertz, just sort of the piano, mid-piano band. But it turns out that Lisa will see these things at much lower frequency. Because our detector is in trouble. I haven't shown you a budget for the noise. But as you go to lower frequency, let's say down to 10 hertz, the ground-based detectors get noisier. And that's because of an effect I haven't told you about at all. I haven't given you a noise budget of the detector. But there's something called it's called Newtonian gravitational gradient noise. Now, I can tell you exactly what that is. It's sort of an interesting noise. It's a noise which we have to learn how to do something about, or only can be done in space. We have all these wonderful ways of getting rid of the seismic motion, because we have what's called the inertial frame to refer ourselves to. We can refer ourselves to the frame that has all the matter of the universe sort of on the average steady, being average steady, moving at no velocity. That frame is identified for us, and it's the thing that establishes the inertial frame for us. So we can make instruments that measure motion with respect to that frame. The thing we can't do is, on the Earth, you have these sound waves running in the crust of the Earth. And what happens is there's a density change here. And let's say here's our mirror. That's the thing I was holding here. Right over here, there's a density change as that wave goes by. There's a refraction, density change, gets thinner, denser, thinner, denser. That density change in the Earth pulls this mirror over to its higher density regions by gravitational forces, just plain old Newton mechanics. And that is a noise that we can't get around because there's no way to shield it. And so we have to, the only way we know how to deal with that noise is to actually go and put seismometers and strain meters and other kinds of devices that can measure the motions of the ground all around us. And people are trying to do that. But that gravity gradient noise may be a limit that takes off like a shot when it gets worse and worse as you go below 10 hertz. And that's the reason why many people are contemplating building a detector in space, because you don't have that noise in space. You have other noises, but not that one.
One last question. Let's see. In the blue, you've had your hand up. Yeah, no, don't look around. It's you. I guess not. Sorry, go ahead.
I can't hear you. You're going to have to stand up.
Please, yeah.
Please stand up. Well, I could only heard what other
Is
gravitational
it possible for gravitational waves to be produced by something other than the collision of two black holes?
Oh, yes, very much so. And examples of that are, well, two neutron stars, for example. We know about those because that's the thing that Holtz and Taylor saw. And we see them when these are neutron stars, not black holes. They're going around each other, and they crash into each other, and they make a black hole. And we think that something called gamma ray bursts are indeed the electromagnetic counterpart of that. Then there are pulsars themselves, the things we talked about in the early part of the talk. Pulsars which have a magnetic field on them, which are squished a little bit. And they're little wobbling footballs. And they radiate because they've been squished together. They're no longer spheres. And as they spin, it's the same. They spin, and as they spin, they wobble back and forth. Why? Because the magnetic field axis may be along this direction, whereas the spin axis may be at another angle, like the Earth. The Earth's magnetic field is at 5 degrees to the spin axis of the Earth. And that makes the squished star wobble as it turns around. People hope, we're looking right now, every time we look for neutron stars that way, individual neutron stars that are radiating. The other thing is just a supernova. Well, okay, the supernova are stars that have exhausted all their fuel, and they collapse on themselves and make a huge display. And they form black holes or neutron stars. And that process has a lot of accelerations in it. But that only occurs in our galaxy once every 30 years, maybe once every 50 years. But those were the first sources we were thinking about detecting. And now that we shouldn't give up on those. It's just that people, I'll tell you what, we were very optimistic 30 years ago. We said, maybe we can detect these because they put out maybe 1% of their rest mass energy in gravitational waves. And it turns out that turned out to be real bunk. It was just plain wrong. And the way that was found out was by in 1987, there was a supernova not too far from us. And we saw that supernova emitted a huge amount of neutrinos. And the neutrinos slowed the thing down. so that they don't radiate gravitational waves so well. So 1% of the energy of a supernova going into gravitational waves is really unheard of. Nobody's been able, ever since that discovery, to model a supernova. But maybe 1 part in 10 to the 5, or 1 part in 10 to the 6 of the energy. And that means that if we get better detectors, and we have them on the drawing boards, detectors that could do this, and see something like 1 or 2 supernova in a year. That would be a very fascinating thing to do. Yeah.
That's a great goal.
Yeah.
It certainly takes something to catch a wave in
It
your
sure does.
field. Thank you so much
You're
for,
quite welcome.
and thank you for a lot of really good questions. Much appreciated. I want to thank NASA and Goddard, Space Telescope Science Institute, Netta Bahcall for the John Bahcall Memorial Lecture Series, and our 10th anniversary speaker.
Oh, good. Thank you for having me.
Thank you.